thank you for that great introduction. Thank you for being here, and thank you, the organizer, to host us in such a place. It's a really nice way to restart the conference season. So, how many of you are designing software architecture? Okay, majority of you. How many of you are running in operation software architecture? I think this talk will interest both of you, so if you raise your hands at one of these two questions, that's probably one of the talk for you. I'm going to talk about resiliency. What is it to resist to failure? And what are the design patterns you can implement in your code to make applications that are a bit more resilient to failure? Have you seen that video before? It has been viral last year or something. So that guy is trying to cross the street. He finds an unexpected obstacle, a fence. Of course, he's doing something very natural, trying to cross the fence. And things can fail. And sometimes they have cascading results on the failure. And unexpected. Nobody that put that fence there was expecting that someone would try to jump over and stop the entire traffic. And that's my favorite part of the video. It's the poor guy is trying to correct the error. Okay. You are building distributed systems. I started building systems when it was one server and one database. Even at that time, it was hard because the database can fail. And remember that time where you have a Java stack trace on the screen saying, hey, you cannot connect to the database. These days, it's not one database. It's dozens or hundreds of microservices that you are trying to connect. And all these things can fail independently of each other. And all these things can fail in an unexpected way. And of course, on your laptop, it works. And taken in isolation, when you're testing your service in isolation, most of the time it works. But let's face it, building a distributed system is hard. And if one thing is sure, is that something will fail. So it's not a matter of knowing where it will fail or how it will fail, it's when it will fail. So it's better to be prepared for that. And I'm going to give you and share a couple of tricks, design patterns, tools that you can use to prepare for the random, prepare for the wild, wild west. You don't know exactly how your API is going to be used, how your application is going to be used. So this talk is about resiliency. Resiliency is the ability for a system to handle errors and eventually to recover from these errors. And recovering might be a full recovery, or it might be also working in partially degraded mode. I'm going to give a couple of examples of application that works with partial degradation of the service, a bit something like this. That's another example of partial service failure and trying to fix the problem without interrupting the service. In a very creative way, by the way. That's my last video. After that, I'm going to go into more technical stuff. But this is so impressive. So the service is still running. Of course, it's not running full speed. We are fixing it without interrupting the service. And in reality, it's a matter of many different things. It's a matter of networking. It's a matter of your data. It's a matter of your infrastructure. It also, of course, depends on your application. That's what I'm going to talk about today. It also depends on people. How many times in your company did you drill the people to react to errors? Are you running game days or some other experiments to just see how the teams are communicating? Are they trained to actually react to production errors? So it's a matter of tools, processes, and people. I'm going to share with you a couple of design principles. And these are not cloud dependent. These are not AWS dependent. You can apply that for on-prem most of the time, maybe not that one. And they are not specific to AWS, so you can really apply that to any type of architecture running on-prem or in the cloud. But if you are running in the cloud, one of the advantages of deploying your application in the cloud is the geographic availability of the cloud. All the cloud providers I know have multiple locations. At AWS, we call that an AWS Regions. I count them this morning while I was in the train. It's 25 as of today, with 4 that we have pre-announced, and 2 that matters for us, European, in Switzerland and Madrid are going to come next year. And how can you use advantage of that? You have to know that at AWS, a region is made of multiple data centers. We call them availability zone. And an availability zone is really like a group of data center which is isolated in terms of errors from other data centers in the same regions. So they are separate by a few miles to ensure that if something terrible happens on one data center, the others cannot be affected by the same risk at the same moment. Different network connectivity, different electricity connectivity. In San Francisco, for example, where there is a high risk of earthquake, they are located on different sides of the big reef. So if one is destroyed by an earthquake, the other groups of data centers are not destroyed by the same risk at the same time. So when you're evaluating your cloud provider, think about that and think about how many data centers they have in what they call regions and how these data centers are separated from each other. Because if they have data centers next to each other, it doesn't really count in terms of high availability. Because if something bad happened to one, maybe the one next door is affected as well. Why does it matter for you? It's because you can take advantage of that infrastructure to deploy your application across these multiple data centers. So typically in the regions, you are going to have, let's take the Paris region right now. You have 3 availability zones, each availability zone made of multiple data centers, and each availability zone are designed to be independent of failure from one to the other. So knowing that, you can deploy your application in multiple availability zones. Instead of deploying all your application in one availability zone, just deploy on 2 availability zones. There is no additional cost for you to do that. You put a load balancer in front of you. The load balancer knows about multiple availability zones and can bring the load to these different availability zones. And believe in the magic of math. When you're deploying in parallel your components, you increase the availability of your application, if the application is correctly designed, but that's for the rest of this talk. So a typical architecture in the cloud, this one is AWS, but once again, it can run on many different large-scale cloud providers. You have a regional level load balancer. That's the entry point for your architecture, for your web app, for your API, for example. And then you deploy on multiple virtual machines. We call them instances. In multiple availability zone. Remember, multiple availability zone equal multiple data center. That's for the front end, that's easy. Most of the time, the hard part is there, it's the database, because hey, you need to have like a master write database, which by definition lives in only one availability zone, but we make it easy for you to replicate, to have read replica or standby instance in other availability zones. So if something bad really happened in one availability zone, which should not happen, but we never know. Earthquake, fire, plane crash, things can happen. So if something bad happens on one availability zone, the load balancer will detect that, will stop sending traffic to your instance, and if there is a database in that availability zone, and you have a standby, then the standby database will detect that the master is not there anymore. It will instantiate as a new master database and continue to serve the traffic for your customer. So that's the most basic things, like the 100, the ABC of high availability in the cloud. Do not put all your eggs in the same basket. Spread your instances, spread your workload across multiple availability zones, maybe over multiple regions as well if you have really high requirements in terms of availability, but that brings other type of challenge I'm not going to talk about today, mostly around latency and data synchronization. So that's my first design pattern. First design pattern is about use the geographic infrastructure that the cloud provider is providing for you. The second one is about timeout and backoff and retries. How many times did you check what are the settings for your timeouts on your different software components? Who did it? Usually only a few, and here as well, only a few of you. Actually, that's a good question. What is the timeout on my application server? What is my timeout on different microservices? How do I manage this timeout, and why is it important? Let's take an example. You have an application, traditional application with an app server, might be a Java application or Ruby or something, talking to a database. And you have a front end that is making connection. You have a connection pool that has TCP connection to your database. And for some reason, the database starts to slow down. Maybe there is a high load on the database or a hardware problem, disk I/O problems. Something is happening to the database. So what's going to happen? In theory, there is a timeout on the client side, and there is a timeout on the backend side. The small poll asking you to raise your hand show me that most of you didn't verify that. And you would be surprised how many systems have, by default, infinite timeout, no timeout. So what's going to happen? Client is making a connection. Connection is consumed to the database. Database slow down. There is no timeout there. So eventually, the timeout on the client side kicks off. And you have a well-written client application. Congrats. The application retries. Oops. So the application will retry. By retrying, it will consume another connection that will not time out. And so it will time out again on the client side. And so on, and so on, and so on. Imagine then you have dozens or hundreds of clients retrying at the same time. What's going to happen? You are eventually going to consume all the TCP connections available in your connection pool. It might be at the app server level. It might be at the operating system level, because you are limited in the number of TCP connections that you can do at the host level as well. So whatever is the technology you're using there, you're going to have some kind of issues there. So set a timeout. And all systems that I know have a possibility to set a timeout. Might be your web server, Apache, IIS, your database, Tomcat, whatever you're using, there is a possibility to set a timeout. And be aware of systems like MySQL that have infinite timeout by default. So check these and be sure that you set a timeout on your JDBC or ODBC connection. If you're developing your own code, you can also factor in timeouts. And in Python, it's super easy with some annotation and a library. You can just decorate one of your functions, giving the timeout and giving the method to execute when the timeout kicks in. If you do that, you can probably avoid the error that I show you just before. What can you do, actually, besides setting the timeout to avoid that type of error? And the answer is by implementing a very simple design pattern, is retry and back off. So retry makes sense, and exponential back off. So wait a bit before retrying. Because if a resource has some availability problem right now, and all the clients retry all at the same time at maximum speed, you're just going to make the problem even worse. You are going to kill the poor database or the poor resource. So wait a bit before retrying. What works well for us, it's exponential back-off. So we wait 2 seconds, we wait 4 seconds, 8 seconds, 16 seconds. It might be milliseconds, of course, depends on your application and the business case. But wait a bit, and every time you retry, wait a bit more to give more clients a chance to get access to the resource. If you do that, eventually the operating system or the application server will release the connection. And so at some point, the client will manage to get the connection again. Of course, if all your clients have the same algorithm for the exponential backoff, you might end up with all the clients trying or retrying the operation at the same moment. 2 seconds after, thousands connection to the database. 4 seconds later, 1,000 connection to the database. And this gives this type of graph. So here we have the time in milliseconds. Here we have the number of calls. Here, everything goes well. Something goes wrong, and the retry strategy on the client starts to kick off. And you see all the clients are retrying at the same time, and you put even more pressure on the resource which is already under constraint. So what works well for us is to add a bit of salt in this retry, to add a bit of randomness. Instead of retrying 2, 4, 8 milliseconds or seconds, do 2, 4 plus a random number, so that all clients are going to retry at different moments, and you are going to spread the retries over time. This is what we call jitter, and this is a graph with a jitter, and you can see that it's a flattened version of that graph. The clients are retrying at different moments of time. So exponential backoff for your retries with some jitter, with some randomness. It sounds complicated when I say it like that, but it's one line of code. Seriously, it's one line of code. This is an example in Python. Sorry, it's a bit low on the screen if you're in the back of the room. But time.sleep, that's a weight. 2 exponent n is the current number of the retry, plus a bit of randomness between 0 and 1 second. So it's one line of code to add that touch of randomness. Another patterns that works well as well when your resources are under constraints is to put a circuit breaker. So instead of calling directly the resource, you call a proxy of the resource. The proxy validates the availability of the resource for you and return some default or return a nice proper error message with correct timeout if something goes wrong. So it's a proxy design patterns, a circuit breaker. The grandfather of libraries implementing circuit breakers, it's Istrix from Netflix. I'm not sure it's well maintained right now, but all the libraries that you can find today, the modern libraries, are inspired by that one. So it's worth having a look at Istrix. Istrix is for Java, and it works with decorator as well, like Istrix commands, and you give the name of the fallback methods. And so it knows that it has to proxy that web service and provide some default value if it cannot reach the service. Another pattern that we are using is health checking. So health checking is to verify if the host is healthy. In a typical application, you have your load balancer, front-end, back-end, and then a couple of back-end services, such as database, caches, email services. What the AWS load balancer are doing, and I guess most of the load balancer are doing that, is before to forward a request to an instance, it checks if the instance is healthy. So at regular intervals, it says, hey, are you healthy? Yes, I'm healthy. Are you healthy? Yes, I am healthy. And it only forwards requests to healthy instance to avoid that a request cannot be served. So when you implement health checks, you have 2 different ways to implement your health checks. The first one are the shallow health checks. The instance just say, yes, I'm there. And of course, the other one is the hard one, is to check all depending systems as well. It might take more time, it might take put more pressure on these different systems. It really depends on your application, which one is best for you. Can you continue to give the service even if one of these is done? It depends on your application. It depends what is the one of these which is done. So when you are planning for health checks and implementing health checks, consider what are the critical resources that your application needs to continue to work. And when the times are becoming a bit harder, when you have problems, be sure to continue with shallow health checks instead of deep health checks, to not put additional pressure on a system which is already struggling. Beware of caches. Cache can be your enemy in terms of health checks. So handling health checks, it's a bit of art on top of science to fine-tune and to get the exact health checks that you need. Another design pattern that we are using at AWS is load shedding. So load shedding is when you know that you are going to have too many requests, just drop a couple of requests up front from the proxy, and just return an error or return cache content or hard-coded content for a couple of customers. Let me explain you that. You know that the latency of a system will increase depending on the number of transactions per second you have. So the more throughput you have, the higher the latency will be, and at some point the latency will be so high that the system will become unusable for end user or for a client. So what if you can define the threshold saying, okay, below that number of throughput, I know that my system is working. I can accept client connection. But above that, I know that my system will fail. So my front-end component, the first component that accepts the connections, maybe a proxy or something like that, maybe it would be reasonable to just drop any additional request to connect to the service at that time, even if it is a valid user. And yes, you are going to piss off a couple of users or service using your backends because you are going to drop and return maybe an HTTP 500 error for a valid request. But is it better to lose maybe 10% of the request there, or is it better to lose the entire service and to not serve any request for any customer? So load shedding is really about rejecting valid connection before your system struggle with too much load. You need to have the guts to do that. I already tried to implement that at some companies where the marketing team say, no, I don't want to reject valid connection. And I was trying to explain that is it better to reject 10% of the valid connection rather than crashing the entire system? And that's a difficult trade-off. I didn't succeed to convince them at that time, so we didn't implement load shedding. If you do that, don't be too optimistic about the load that you can take. It's better to start to reject too soon than too late, because if it is too late, you will affect all the clients of the service. Try to find the right metric. Is it the number of connection? Is it the CPU? No, probably not. But try to find, and that's most of the time business dependent, to find the right metrics to observe and to monitor. Don't just reject a request. I give an example of HTTP 500, but instead of rejecting a request, you can serve pre-compute content, cached content, or the same content for everybody. Imagine that you have a news service. Maybe you can fetch a couple of news from the cache instead of returning no news at all. And beware with the health checks. Be sure to not drop the traffic of the health check. Because if you do so, the load balancer, whatever proxy is using the health checks in the front, will consider your service as being dead and will stop sending all traffic to the service. So the health checks must be prioritized over the other type of request in case of load shedding. Netflix is doing that really well. I guess you all use Netflix. You have all these banners with different suggestions that are made for you. But if the service is not available, they will just return hard-coded value. The same for everybody, but you will not notice. And the front end can continue to accept and to propose you video that you can click and probably start to view. When you don't do that, and I love Reddit, I don't want to criticize Reddit, you might end up into a user interface like that. And you saw that at many different places as well. Sometimes the service is not answering, so you have the frame, but you don't have the individual service. And it's so easy to return some pre-hash content, predefined, pre-compute, cache content instead of white pages. Think about the user experience. So to finish, my preferred one is sharding, isolation. So sharding is not a new concept. I don't know if any of you built a boat already. I didn't, but when you build a boat, you create different compartments. So if you have water in one compartment, in general, it's supposed to not propagate across the boat. So you can do that with your fleet of application server or front-end server as well. So instead of having one load balancer and 100 server in a common pool, why not isolate your server by compartment, by cells, to shard your user? Of course, for that, you need a routing mechanism. You need a kind of front-end proxy in the front that will assign each of your users to a different cell. And a cell might be a load balancer with multiple instances, or it might be just a couple of instances that receive traffic from a front end. But the idea is to assign a group of users to a group of cells. So the first 3 users, I assign them to cell 1 and cell 2, and the rest in the current order. And if cells are independent from each other, if something bad happened to a cell, it will only affect the customer that are assigned to the cells. And that's why so many times on large service, such as the ones from Google, from Amazon, you go on a website and your colleague says, hey, the console is not working for me. And you, on your laptop, you refresh, and yes, for me it's working. It's probably because you are going to different cells in the backend. So what happens if a customer is using a cell, and the customer does something which was not planned, bad request, something that you didn't plan for, we call that a poison pill. That's the request that kills your system. There is a bug in your system, and that request kills the system. So of course, the client is well developed, so the client will retry, and eventually exhaust all the servers that are available in that cells, killing the cell, and killing the cells for all the customers that are there. But because a customer is assigned to multiple cells, customer will be redirected to cell 2. But the bad customer, or at least the bad request, will be reassigned to cell 2 as well. And so after a while, cell 1 and cell 2 will die. You will lose a couple of customers, but at least all the others can continue to work unaffected with the problem. So you isolate the problem. You prevent the problem to propagate to your entire fleets of machines, and your service is still up and running to continue to serve your customer. So what is the metric for there? It's called the blast radius. What is the effect of, what is the effect of a blast? What is the blast radius? So how many customers are going to be impacted if you lose a cell? What are the functionalities that are going to be impacted if you lose a cell? There is a way to make it even better. It's to assign customer to cells randomly. Because in my previous example, I had the same customer assigned to cell 1 and cell 2. So if I lose cell 1 and cell 2, I have the same groups of customer that is affected. But once again, randomness is my friend here. What if I assign customer to cells randomly? In this example, the customers are not sharing the same cell. So here, that little guy is with the bonnet and the corn, and here it's with the trèfle and the bells. Sorry for the French, I don't know how to say that in English. So if that guy continue to send the poison pill, the request that kills your server, it will eventually kill cell 1. But the rabbit is still going to be served by cell 4, the corn is still going to be served by cell 2. So eventually, when the bad guy will continue to kill another cell, these two customers are still served by another cell. And these two customers are still served by another cell. So the only affected customer there is actually the one sending the poison pill. The other might be affected as well, maybe a loss of performance because you have less capacity, they are served by one cell instead of two. But at least you contain the problem within a part of your system and not the totality of your system. And once again, randomness and math is our friend. The more cells you have, the least probability there is to overlap two customers in the same cell. And if you remember probability and factories and playing with all that at university, the more nodes you have, depending on the size of the cells, the less probability there is to have two customers overlapping on one single cell. So you need a fault-tolerant client that retries, but I guess you get that already, and you need some kind of routing mechanism to be able to assign a customer to a cell. Netflix developed their own proxy to do that, so they have a very lightweight proxy in the front of the rest of the infrastructure that does this assignment. You can do that with application level load balancer, HTTP load balancer. If you had specific requests in your HTTP header or in the query string, like the customer ID, you can hash that, and depending on the hash, route the traffic to one cell or the other. So that's a bit of configuration that you need to apply to be able to implement this type of cell sharding. So that's the routing mechanism there. And finally, experiment, test that, try that. Don't wait for the problems to be in production before testing your system and your people. At Amazon, we make game day. At Netflix, they have developed a whole set of open source tools called the chaos monkeys that are able to simulate failure on their systems. So chaos engineering is the heart of stressing a system to observe how the system will react under stress. Netflix and Amazon, we do that in production. Don't start with that. Start with controlled environment, your test environment. And experiment. So chaos is not a matter of bringing chaos to your system. The name is a bit misleading there. Chaos is about experimenting. Define what you want to test, what are your hypotheses, define how you're going to test, execute the test, and observe how the system is performing. Are you monitoring the correct metrics? Are you reporting the correct alerts? Is your team correctly trained when that alert, do you know if the people knows what to do when that specific alert arrives? So chaos engineering is something extremely structured. The goal is to not bring chaos into your systems. It can start really, really easily with failure injections in your application, or you can inject failures at host level. What if you exhaust all TCP connection on a host? What if you exhaust the memory on a host? What if you exhaust CPU? And there are tools that you can use on Linux and Windows to generate a lot of CPU or generate stress on the memory of the machine, and just observe how your system is going to behave. Recently, a few months ago, we released a tool to help you to do that. Since 15 years at AWS, we try to bring more availability in our tools. This one is actually the opposite. This one is to break your infrastructure. It's called Fault Injection Simulator. It allows you to inject fault at host level or at application level into your configuration and to monitor how your system is behaving when there is such a fault, to generate alarm, and maybe if there is an impact on production, if you do that on production, to automatically stop the experiment and revert back if something goes really bad for your customer. So try, experiment with chaos engineering. Don't start with production, of course. If you want to learn more about all this, there is the well-architect framework from us. So if you are deploying on AWS, and that's probably the only specific slide for AWS, if you're deploying on AWS, the well-architect framework, it's a set of questions that will make you think about different aspects for different pillars like cost optimization, performance, but there is one here that is in linked with this talk. It's reliability. We are going to ask you a question. Did you do that? Did you do that? How did you do that? And depending on the number of yes and no answer, we'll give you a reliability score for your architecture. So you can measure where you are, you can take actions, and later measure the improvements that you are making on your architecture in terms of reliability. This talk has been heavily inspired by the work of my colleague Adrienne, that has a blog with tons of really good articles. So if you are interested about reliability engineering, have a look at Adrienne's Hornsby blog, and I'm going to share the slides with you. I'm going to give you a URL for the slides. At Amazon, we have also the Builder Library. It's a collection of articles about how Amazon is doing things. We are building one of the biggest websites of the planet since the last 20 years. So obviously, we learn a lot about what is it to bring high availability to a public service on the internet. And this is a collection of articles written by senior principal engineers at AWS. So like half-god type of engineers that we have, the ones that are designing the systems, that are responding to failures and designing systems to avoid failures in the future. So plan for the worst, because it will happen. You don't know when, but start to experiment small on different parts of your system. Start today. Don't wait before trying to test the reliability of your different services and applications. You can find me on different places: Twitter, LinkedIn, Twitch, YouTube. Video, it's mostly in French. I'm the host of the AWS podcast in French. If you like podcasting and podcasting about the cloud, search for AWS, le podcast AWS en français. That's the name. It's a weekly podcast about AWS. And if you want the slides, it's there, speakerdeck.com/sepsto. And if you have 2 minutes right now, you can give me a feedback about this talk, what you think about the talk, how we can improve it in the future. You just scan that QR code, it brings you there. If you don't trust me for the QR code, you can type that address and the code there. You have 3 anonymous questions, and you can get a $25 service credit that you can apply on your AWS account, and it will be discounted from your next bill. And that being said, I have 25 seconds left.
Right on time.
Thank you.
Thank you very much.